During the year of the Gemini program from January 1964 through January 1965, Gemini moved steadily toward its primary goal of a flight of a two-man spacecraft. On the 7th of April, Gemini began counting down for the first step. Gemini 1, unmanned, was being fueled for orbital flight. It would not be recovered. The major objectives of this flight were to prove the compatibility of the launch vehicle and spacecraft, to qualify the launch vehicle systems in flight, and to evaluate the launch complex. Checkout proceeded into April 8th. Watched closely would be the performance of the Gemini launch vehicle in the early stages of ascent. It incorporated design changes to correct the longitudinal oscillations encountered in early flights of Titan II. There were no major holes in the countdown. Within 1 second of the scheduled time, Gemini number 1 lifted smoothly off the pad. It rose high above Cape Kennedy, following the programmed flight trajectory for orbit. 5 minutes and 37 seconds later, spacecraft and stage 2 of the launch vehicle entered orbit as planned. All purposes of the flight were attained. Launch vehicle oscillation was lower than predicted and well within limits for manned flight. GT-1 had now become the 133rd successful major launch of the National Aeronautics and Space Administration. The first Gemini flight inaugurated a concentrated year of successful testing, flight qualification, and hardware production. The second spacecraft moved to Complex 19. Before it was to be launched, Spacecraft 3 joined it at the Cape. The backup flight craft, 3A, was undergoing final tests by the contractor. It would first be used for altitude chamber tests. Concurrently, spacecrafts 4, 5, 6, 7, and 8 had moved into the White Room for final assembly and systems tests. Spacecraft 9 had started structural work on the cabin and rendezvous and reentry sections. Structural weld assembly had begun on Spacecraft 10. 3 Gemini launch vehicles, 2, 3, and 4, underwent final testing at the contractor's facility and were accepted for delivery. They were followed by GLV-5, which was erected in the vertical test building, and by GLV-6, which was in pre-splice installation. Agena 5001 was successfully static fired at Santa Cruz, California, and scheduled for delivery as a test bed vehicle for facilities and equipment checkout. Agena 5002, which would be the first target vehicle launched for rendezvous, was undergoing modifications peculiar to the Gemini mission. Standard Launch Vehicle number 1 was accepted at the Cape in December. It was erected for pad validation checks. Astronaut training was reinforced by the delivery of essential hardware: 2 mission simulators, a translation and docking simulator, and a part task trainer. During the year, crews for the first 2 manned missions were selected. The program had given them the tools to prepare for the major Gemini objectives: a more sophisticated 2-man space mission which would demonstrate long-duration flights up to 2 weeks, maneuvering in space to rendezvous and dock with another vehicle, and performance of space tasks outside the vehicle. A glance at the spacecraft reveals that it may be divided into 2 main sections: the reentry module and the adapter section, which mates with the launch vehicle. The adapter houses many of the spacecraft systems and the retrograde rockets. We may therefore subdivide it into retrograde and equipment sections. A full-scale engineering mock-up of the equipment section shows that it contains the electrical power source, elements for environmental control, and electronic components. 10 of the 16 thrust chambers used by the orbital attitude and maneuvering system are also located here. The remaining 6 thrust chambers in the adapter are housed in the retrograde section, along with the 4 solid propellant retrograde rockets. The reentry module has 3 sections. The first is the cabin, a pressure vessel with 2 hatches for astronaut ingress and egress. Each hatch has a window. The interior of the cabin provides seating, instruments, and control panels for the command pilot and pilot. It also contains food, water, a waste management system, and survival equipment. Forward of the cabin is the reentry control section. It houses the propellant tanks and thrust chambers of the reentry control system. The final section of the spacecraft is the rendezvous and reentry section. It provides latching points for physically docking with the Agena target vehicle, a rendezvous radar package, and it houses the 3 parachute assemblies, drogue, pilot, and main parachutes. Only the cabin and reentry control section are recovered from a flight. All others are jettisoned during some phase of the mission. At McDonnell Aircraft Corporation, St. Louis, Missouri, sections of the spacecraft are manufactured on an assembly line basis. The sections are then moved into a clean room area for systems installation, systems tests, and final mating with other sections. All Gemini contractors follow clean room controls where external contamination can compromise the reliability of a part. After a component passes inspection in a contractor's clean room, the environment is maintained by sealing it in a plastic bag. It will be shipped to McDonnell, where it is tested again and installed in the Gemini spacecraft without breaking clean room integrity. As the individual sections move through workstations in the White Room, spacecraft systems are installed and tested. Each component is tested in the subsystem, then in the system stage. NASA engineers and inspectors monitor all tests, write up discrepancies where necessary, and check the cleanup. After the systems are tested in each section, the spacecraft is joined for the first time. Testing begins again, culminated by a simulated flight mission. Only after the spacecraft has passed the final cleanup after this test is delivery made. A spacecraft in launch configuration weighs about 7,000 pounds. The weight will vary considerably according to the experiments to be conducted on board and other requirements. The spacecraft is approximately 19 feet long and 10 feet in diameter, where it mates with the launch vehicle. The Gemini launch vehicle is a modified Titan II procured by NASA through the Air Force. It is man-rated to ensure the safety of the crews. Important among the modifications made to the GLV for manned flight is the addition of a backup flight control system. Both Stage 1 and Stage 2 are controlled in flight by gimbaling the thrust chambers of the Aerojet engines. If the primary flight control system malfunctions, switchover is made to the spacecraft's inertial guidance system and to the backup autopilot. A malfunction detection system, here being monitored by test consoles, has also been added to underline safety. The MDS monitors the performance of all subsystems of the launch vehicle and displays a warning of abnormal conditions on the crew console. The complete malfunction detection system was flown open loop on the 2 unmanned flights in this period. Contractor to the Air Force for the launch vehicle is the Martin Marietta Corporation. The fuel and oxidizer tanks for the 2 stages are manufactured at Denver, accepted by the Air Force and NASA, and then airlifted to Baltimore for splicing, manufacturing assembly, installation of the Aerojet engines, and testing. A final checkout of all systems is made in a 100-foot vertical test building, whose center stand permits erection of both stages in tandem. A simulated countdown and flight trajectory of the launch vehicle, with all systems operating except the engines, concludes weeks of intensive vertical testing. A vehicle acceptance team, composed of Air Force, Aerospace, and NASA members, review all test results. Discrepancies are noted. Upon their resolution by the contractor, the vehicle is signed off for delivery to Cape Kennedy. GLV-4 was accepted for delivery on December 13, 1964, and was followed in vertical testing by GLV-5. The 6th launch vehicle has been delivered from Denver, and it is in the pre-splice installation stage. After the first successful flight, major emphasis was placed on the launch of the 2nd spacecraft. Unlike the orbital mission, GT-2 was suborbital and would be recovered. As such, the primary purpose was to demonstrate that the reentry module would withstand maximum heating conditions of reentry. An ablative heat shield covers the larger diameter end, which enters the atmosphere first and bears the greatest thermal and pressure stress. Dish-shaped, it is manufactured from fiberglass honeycomb filled with silicon elastomer. The remaining outer shell of the cabin is covered with shingles of Rene 41, a heat-resistant alloy. The rendezvous and reentry section is constructed of a titanium alloy with outer shingles of beryllium. Beryllium is an element with the property of absorbing unusually high inputs of heat without rapidly increasing in temperature. A parallel purpose of GT2 was to further qualify the spacecraft systems for the first manned flight. Electronic simulators were included in the flight to measure many elements of crew participation. Among the major spacecraft systems are environmental control, electrical power, propulsion and control, guidance and navigation, communications and instrumentation, sequential system, pyrotechnics, escape system, and landing system. An important element of environmental control is the coolant system. This is, in reality, a thermal balance control system. For it not only cools the cabin, suits, and equipment, it also heats the cryogenically stored liquids, converting, for example, liquid oxygen to a gaseous state, which the astronauts can breathe. A coolant fluid is pumped from a reservoir through a closed-loop system. It flows through cold plates on which are mounted the electronic and electrical equipment, absorbing heat. It also flows through the space radiator. The space radiator is an integral part of the spacecraft structure in the adapter, equipment, and retrograde sections. It aids in maintaining proper temperature of the cooling liquid by causing it to lose heat in space. The environmental control system also furnishes oxygen to the cabin and pressure suits. In addition, it provides for waste management and supplies food and drinking water. Drinking water will be carried on the first manned flights in storage tanks in the cabin and adapter sections. On later flights, drinking water may be supplied as a byproduct of fuel cells, which will be the main source of electrical power. Fuel cells produce electrical power by uniting oxygen and hydrogen through catalytic electrodes. 2 such fuel cell batteries will be the main electrical source during the longer missions of 7 and 14 days. Silver-zinc batteries will supply supplementary and backup power. The fuel cells are in the adapter section. When this is jettisoned, the spacecraft switches to 4 of the backup batteries in the cabin section. Major elements of the propulsion and control system were tested by the flight of GT2. These were Orbital Attitude and Maneuver System, or OMS, Reentry Control System, RCS, and Attitude and Control Maneuver Electronics, which conveniently shortens to ACME. The Orbital Attitude and Maneuver System will give the command pilot an onboard capability of making maneuver changes as well as attitude and velocity changes after separation from the launch vehicle. The system has 16 thrusters located in the equipment and retrograde sections of the adapter. 8 thrusters producing 25 pounds of thrust control the spacecraft in pitch, roll, and yaw. The remaining 8 thrusters, producing either 100 pounds or 85 pounds of thrust, control the spacecraft in the vertical, up and down, and horizontal, left and right direction. They also speed up or slow down the spacecraft. Using these, Gemini can make orbital plane changes as well as orbital altitude changes to effect a rendezvous and docking maneuver with a target vehicle. During the year, the OMS system was thoroughly qualified by ground test for flight in GT2. The command pilot jettisons the adapter prior to re-entry, and the OMS thrusters are lost. He then switches to the re-entry control system to maintain attitude control. This has 2 independent systems. Each consists of 8 25-pound thrusters. The re-entry control system was qualified by a ground test program during the year. It would undergo a thorough flight test during the re-entry mission of Gemini 2. Attitude and maneuver electronics direct firing commands to all thrusters. Commands may be initiated automatically by the spacecraft guidance system or manually by the crew. The guidance and navigation system is packaged in modular units and housed in the spacecraft cabin and rendezvous and recovery section. It includes a general-purpose transistorized computer of the binary digital type, an inertial measurement unit, horizon scanners, an L-band radar for rendezvous and docking maneuvers, and a time reference system providing time to go for mission events, and a Greenwich Mean Time clock. The inertial measurement unit provides attitude data with either inertial reference from the inertial platform or Earth vertical reference from the horizon scanners. It furnishes attitude and velocity information to the spacecraft computer and to the console displays. Located within the right crew station, the computer has a solid-state random access memory capable of storing over 160,000 information bits. Both the pilot and ground control can feed new information into the computer, keeping it updated with the mission at all times. It furnishes data to the command pilot for his use in controlling re-entry and landing the spacecraft within close limits of a designated point. Another important function of the computer is to receive and process data from the L-band radar during rendezvous. The Gemini spacecraft maintains contact with the ground through three systems: voice communications, beacons, and telemetry systems. Telemetry monitors both equipment function and the biomedical condition of the crew members. Over 300 separate measurements are recorded and monitored by ground receiving stations. Voice communication is maintained between the ground and the crew by high-frequency and by ultra-high-frequency transmitters receivers. There are two systems, one of which is a backup. Three types of tape recorders are included in the communication system: voice, biomedical, and data. There are two voice tape and two biomedical tape recorders in the cabin. They furnish a record of portions of the mission for later detailed study. A continuous record of systems performance is kept by the data tape recorders, which will be particularly valuable for intervals when the spacecraft is out of contact with ground receivers. On command over a station, data recorders will dump this information and begin re-recording with a clean tape. There are 4 beacons: a recovery beacon, which operates on the international distress signal during landing and recovery; acquisition aid beacon, primarily to help in tracking the spacecraft in orbit; and C-band and S-band beacons. The C-band beacon furnishes accurate tracking information to the ground stations from liftoff to jettison of the adapter. The S-band beacon is a backup system. The command pilot controls critical events during the Gemini mission through the sequential and pyrotechnic systems. Chief among these mission events are separation of the launch vehicle and spacecraft, separation of the adapter equipment section, firing of the retrograde rockets as a backup after the clock initiates the signal, and deployment of the parachute landing system. All sections are separated by the detonation of pyrotechnic devices. The solid propellant motors of the retro rockets are ripple-fired by the sequential system at 5.5-second intervals when used for normal re-entry, and salvo-fired for high-altitude aborts. There are 2 abort conditions: at high altitude and low altitude. At high altitudes, the command pilot shuts down the launch vehicle with the abort handle and waits 5 seconds. He then separates the spacecraft from the launch vehicle, initiates re-entry, and flies the spacecraft in. At the proper time, the parachutes are deployed as in a normal landing. At lower altitudes, the ejection seat is used for abort. Above 7,500 feet, the free fall of the astronaut after seat separation is first stabilized by a ballute, or balloon-type parachute. Successful ballute tests from 12,500 to 35,000 feet have been held. Indicated airspeed was 110 knots. 6 dummy and 17 human drops were made in this period. Ballute diameters of 3, 3.5, and 4 feet were tested. The 4-foot ballute produced the lowest rotation rate and was chosen for the flight configuration. The ballute separates at 7,500 feet, and the pilot's personnel parachute is automatically deployed slightly below 5,700 feet. It can also be deployed manually. The seat is manufactured by Weber Aircraft. Each seat is ejected individually by a rocket catapult actuated by hot gases that result from blowing the cabin hatches. Extensive testing of the seat ejection system was conducted throughout the period of this report. 3 types of tests were run. Rocket sled tests at Naval Ordnance Test Laboratory, El Centro, California. Simulated off-the-pad tests. And seat ejection from an F-106B aircraft. Although seat ejection was still in qualification testing during this report period, subsequently the system has been successfully tested under actual flight conditions from an F-106B. The final Gemini system, which we shall consider, is the landing system. 3 parachutes are used during a manned mission: drogue, pilot, and main. The high-altitude drogue parachute is deployed by a mortar at approximately 50,000 feet. The drogue parachute has 2 functions. It stabilizes the reentry module and deploys the pilot parachute. The pilot chute separates the rendezvous and reentry sections from the reentry module. At the same time, it deploys the main parachute, which is first reefed to reduce the initial shock. After the main parachute is fully inflated, the spacecraft shifts from a 1-point to a 2-point suspension. This positions the reentry module in the proper landing position with its nose 35 degrees above the horizon for landing in water. Continuous astronaut training parallels Gemini hardware development. We can distinguish 4 areas of emphasis in astronaut training: monitoring and evaluation of engineering design and hardware, test participation either as observer or active subject, flight simulation, and formal academic courses in the basic disciplines underlying space exploration. The future Gemini pilot comes into the program as a trained engineer-scientist. He acquires a particular vantage point as an astronaut to share with other Gemini engineers. Much of the astronaut's time is scheduled for visits to contractor facilities, familiarizing himself with the hardware, and participating in tests. Test participation is a major area of astronaut preparation for a mission. Astronaut James Lovell, along with NASA engineer Gordon Harvey, were the subjects for the first seaworthiness test of Static Article 5. Held in the Gulf of Mexico on April 4, 1964, the test sought to demonstrate the seaworthiness and stability of spacecraft structure during a delayed post-landing recovery. The test would also check out the onboard systems, particularly communications, electrical, and environmental control. It would study the physiological reactions of the subjects under the constraints of spacesuit, cabin, and sea conditions. After 2 hours, the test was terminated because of operational deterioration of some equipment in the spacecraft. A post-landing inspection revealed corrosion in the environmental control and electrical systems. NASA and McDonnell crews reworked the spacecraft and went back into the Gulf ready to run a successful test. Wind that day was approximately 10 knots and rising, and a hurricane threat eventually terminated the test. But it had run 16 hours and 35 minutes, sufficient time to demonstrate that the onboard systems would now function well in a delayed recovery. Although the astronauts, Lovell and Bean, were uncomfortable because of the temperature within the spacecraft, a later test confirmed that this can be improved by partially opening the cabin hatch and by removing the pressure suit after 2 hours. The Gemini pressure suit is an advanced design of the earlier model. The suit has an improved circulation system and incorporates other changes, chiefly in the helmet and glove design. An outer layer of nylon and mylar replaces the aluminized coating. It offers insulation and protection against cold and space particles during the extravehicular tasks planned for later missions. Astronaut Schweikert conducted an 8-day evaluation of the suit. He flew in a jet aircraft to test it under high-gravity conditions, underwent flight simulation in the mission trainer for 4 days, and wore it during centrifuge tests at Ames Research Center. On October 26th, he removed the suit for the first time in 8 days. Biomedical instrumentation had functioned satisfactorily. The suit design presented only a minor moisture problem in the glove area, which has since been resolved. The most important single piece of hardware which the astronaut uses to prepare for a flight is the mission simulator. The 2 Gemini mission simulators were delivered to NASA during the year. The first, stationed at Cape Kennedy, has the GT-3 configuration. On November 9th, the prime flight crew for that mission, Command Pilot Virgil Grissom and Pilot John Young, began training on the Cape Kennedy simulator. Command Pilot Walter Schirra and Pilot Thomas Stafford are the backup flight crew. The mission simulator is also tied in with a control center and tracking network to provide simultaneous training of flight controllers. The next month, the second simulator in the GT-4 configuration was operational and located at the Manned Spacecraft Center. Chosen for the second flight, planned to be a 4-day mission, are Command Pilot James McDivitt and Pilot Edward White. The backup flight crew is Command Pilot Frank Borman and Pilot James Lovell. The simulators are computer-driven and controlled by an instructor at the console. The instructor can program a part of the mission or the entire mission from pre-launch to post-landing on tape. Critical portions of the mission can be rerun and emphasized. Problems and errors unknown to the astronauts can be introduced at any time by the instructor. The crew must immediately recognize the problem, evaluate it on the spot, and take corrective action as though faced with that problem in actual flight. Crews for GT-3 are scheduled for approximately 120 hours of mission simulator training. This may be compared with the estimated 5 hours of the mission itself. Training in rendezvous and docking was made possible with delivery of the Gemini Translation and Docking Simulator at the Manned Spacecraft Center in August. 2 separate pieces of hardware are involved, a full-scale model of the Gemini crew station and the docking end of an Agena target vehicle. Both are mounted on steel rails supported by air bearings. The trainer simulates the last 100 feet of a rendezvous and docking mission, and the pilot is again faced with a probable introduction of errors in the programmed run by the instructor before he completes a successful docking maneuver. Progress that the Gemini program had made in the first half of the year brought GT-2 to the launch pad in July. Then suddenly, unusual combinations of foul weather hit the Cape area, electrical storms, hurricanes, and high winds. It was unique in the launch history of the Cape. Lightning struck in the near vicinity of the GLV on August 17th. Although the launch vehicle was not damaged structurally, a thorough systems check was mandatory, and many systems were replaced. 2 hurricanes swept in from the sea and over the launch complex before the checkout was completed. For safety, the vehicle was twice de-erected and stored in a hangar. GLV-2 was checked out for damage and recycled in test. After an attempted launch on December 9th was automatically shut down because of a primary hydraulic system failure in stage 1, the final countdown for GT-2 launch began early in the morning of January 19th. At 4 minutes past 9 a.m. Eastern Standard Time, the launch vehicle lifted from the pad and began the powered phase of downrange flight. Some 2.5 minutes after liftoff, the booster engine cut off and staging occurred. The sustainer engine then propelled the spacecraft to an altitude of 98.9 statute miles and a maximum velocity of 16,708 9/10 miles per hour. Since this was a suborbital mission, re-entry procedures began after separation of spacecraft from the second stage. An onboard camera looking through the spacecraft window gives us an astronaut's view of re-entry. The film is reproduced at 4 times normal speed. A steep trajectory was selected for GT-2. In this trajectory, the heat shield and afterbodies undergo higher temperatures, but for less time. Therefore, the heat shield was reduced in thickness by 50% to simulate a longer re-entry time. The spacecraft is oriented for retrograde, and the rockets are fired. The retroadapter section is jettisoned. The thrusters of the re-entry control system fire placing the spacecraft in a constant roll rate of 15 degrees per second. We are now reaching the critical period of re-entry when the heat builds up. A roll rate of 15 degrees cancels out normal spacecraft lift. Starting from re-entry velocity of Mach number 25, temperature of the atmosphere immediately in front of the heat shield builds up to approximately 6,000 degrees Fahrenheit. Temperature of the bond line between the shield and the structure was measured at 225 degrees. It was designed to withstand over 500 degrees. The roll rate now stops. The white shafts of light on the screen are thrusters firing to stabilize the spacecraft. In the GT-2 landing sequence, only 2 parachutes will be used. The drogue parachute is omitted. As we reach the parachute recovery stage, the 6-foot pilot parachute deploys, pulling away the rendezvous and re-entry section and deploying the main parachute. The spacecraft shifts to a 2-point suspension from the parachute and floats gently down to sea. As Department of Defense recovery forces waited along the flight path, the spacecraft landed about 20 miles west of the USS Lake Champlain in the prime recovery area. It had traveled 2,127 statute miles in little more than 19 minutes. Navy frogmen drop into the sea and attach a flotation collar to the spacecraft for additional stability. Other helicopters searching the area located the rendezvous and re-entry module about a half-mile from the spacecraft, and it is retrieved for study. The Lake Champlain, now in the area, pulled alongside the spacecraft. At 10:45 a.m., it lifted the spacecraft from the water by crane. In the days that followed, detailed analysis of the spacecraft confirmed the first impressions of NASA engineers on the deck of the Champlain. The mission, GT-2, was a success. Spacecraft 2 had been taken from the water without leaks and was structurally sound. It had withstood a re-entry trajectory planned to create maximum heating on both the heat shield and afterbodies. There was practically no damage. All major onboard systems were flight qualified. Exceptions such as drinking water, food, and waste management would be independently qualified by other means before the flight of GT-3. The first manned flight was now imminent, supported by the results of 2 successful unmanned flights. Gemini 3, received at Cape Kennedy on January 4th, was being prepared to tackle the main objectives of the Gemini program. Gemini will be our first space program to fly long-duration missions and to develop techniques of rendezvous and docking necessary for lunar landing. Gemini prepares the foundation for the advanced spaceflight missions to come.